Okay, in this video I'm going to talk about the Ceva's theorem. So basically the theorem is a criteria when the lines connecting the vertices of a triangle with some points at the opposite sides, or more precisely on the lines containing opposite sides, intersect at a single point. So if we have the triangle ABC and this we denote as DEF, so then the theorem states that so the lines AD, BE and CF intersect at a single point, or all three of them are parallel to each other, or all three are parallel to each other if and only if the following ratios, so the product of these ratios, so BD over DC, so let me first write it, then I will explain. So multiplied by CE over EA multiplied by AF over FB. So if this product is equal to 1, so this product of ratios is equal to 1 if and only if these three lines AD, BE and CE either intersect at a single point or all three of them are parallel to each other. So now about the ratios. So here notice that we take the vectors and not just the segments, and this is to capture the sign. So so BD, so like just to consider one of them to explain it more in detail. So BD over DC, so these two vectors, right? So BD over DC, this is equal either just BD over DC or minus BD over DC, depending on the direction of this vector. So it's equal just to the ratio of the segments if the vectors, if BD and if the vectors BD and DC are in the same direction. And these two vectors are on the same line, so we can talk about direction. So like there are only two possible directions, either they are they look in the same direction or in the opposite direction. And so if BD and here it's DC, DC are in the opposite direction. So the opposite direction, it can happen when the point D is basically on the extension of the segment, not on the segment DC itself, but on the extension. So if point D is somewhere here, then then we have the vector BD like this and the vector DC like this, so they look in the opposite directions. So then we would have the minus sign. So that's how we define the ratio of the vectors. That's why we put the vectors here. So okay, so let me return the point D in the original place. So now about this product of the ratio, so how to remember this. So basically we start from some vertex of the triangle and we move, let's say, clockwise over all the sides of the triangles and vertices. So we take BD to DC, so we move here and then from C, so we arrived at C, then from C we move to by the side CA, so we move to the E, and then from E to A, like this, right? So we take CE over EA, and then by the last side we move from A to F, and from F to B. So like this we take, like starting at B, we move clockwise by all the vertices of the all the sides and all the vertices of the triangle. So that's how we take this product of the ratios. So it must be equal to 1. So okay, so let's consider the proof. Okay, so first we prove in the direction that, like, we assume. So we assume that the lines intersect at a single point, that the lines intersect at single point or parallel, and we need to prove that they we need to prove the equality of the product of the ratios. We need to prove the equality. Okay, so the case when they are parallel, so this would be considered separately. So first we take when they are intersect at a single point. And like even here we restrict for now to the case where all the points are on the sides of the triangle and not on the extensions of the sides. So this would be, so when they're on the extensions it would be proved similarly. The proof is similar. So A, B, C, D, E, F, and so we will use the areas of the triangles. So like let's consider the ratio BD over DC. So in this case, when it's all in the when the points are on the sides and not on the extensions, we drop the vectors, and it's just the segments. So the ratio of the segment BD and DC, so this is equal to so we consider two triangles, so this triangle and this triangle. So these two triangles, the sides, so the sides B, so the sides BD and DC, they lie on the same line, and the vertex will denote this vertex by O, and the opposite vertex is the same. So in this case, the ratio of the areas, so because the area of a triangle, so like if we have a triangle, the area of a triangle, so if this side is A and this the altitude is H, then the area of the triangle is equal to 1/2 of H and A, right? So in this case, so if we have the altitude is is common between these two triangles, so so let's write the area of the triangle BOD is equal to 1/2 of H, so this is H, the altitude multiplied by BD, and the area of the triangle COD is equal to 1/2 H CD. So when we divide one area by the other, like so the area of triangle BOD over the area of the triangle COD is equal to 1/2 HBD over 1/2 HCD. So 1/2 H cancel each other, and it remains only this ratio, BD and CD. So the ratio of these areas is equal to exactly BD over CD. So this is equal to the ratio to the BOD over the area of COD, right? On the other hand, we can do the same argument when we take this large triangle. So this large triangle and this large triangle. So the triangle, so they again have the same. The sides BD and DC lie on the same line, and the opposite vertex is the same. So the ratio is again the same. So the area of triangle BAD and the ratio of the triangle CAD. Right, so now I'm going to remove what we don't need anymore. So I claim that this is now equal to we can subtract. So we can subtract from numerator and from denominator. So this numerator on the second fraction to the subtract the numerator of the first fraction. So the area of the triangle BAD minus the area of the triangle BOD over the area of the triangle CAD minus the area of the triangle COD. And here I use like a simple identity that if we have, let's say if we have the number t that is equal a over b at the same time c over d, so from this it follows that t is also equal to a minus c over b minus d. So we can subtract the numerators and denominators. That's exactly what I wrote here. So how to prove this? Well, simply from the first we have that TB is equal to A and also TD is equal to C, right? Because like we multiplied by like this equality by B and T equal to CD multiplied by D. So, and this equality would be equal to, would be equivalent to T over B minus D equal to A minus C. This equivalent to TB minus TD is equal to A minus C. Right, so TB is equal to A, TD is equal to C. So this is equal to A, this is equal to C. So this is exactly true. So this equality is true. Therefore, by the equivalence, we get that this is also true. T is equal to A minus C over B minus D. So, and the question mark here now we can remove. So, well, this is just a simple, well-known identity. I just wanted to quickly prove it here. So, okay, so we get this, and now we look at the picture. What is BAD minus BOD? So let's BAD, this triangle, minus BOD. So the difference between them is exactly the triangle BAO. So this triangle that I highlight in black. So the difference, so this is equal to, so the numerator would be the area of the triangle BAO. And the denominator would be the area, similarly, the area of the triangle CAO. Yeah, so that's what we need. So the ratio of BD and DC is equal to this ratio of the areas BAO and CAO of the triangle. So now we similarly have the other ratios in the equality. So to recall the equality that we have there, so the equality is this. So let's rewrite it. So BD over DC multiplied by CE over EA multiplied by AF over FB. So BD over DC we just calculated. This is this ratio. So this is, let's write it. Yeah, so this is the ratio of the triangles, of the areas of the triangles BAO over CAO. So the second the second ratio similarly can be calculated as the ratio of the areas so it would be CBO over the ratio of ABO. And the third ratio, so this AF over FB, this would be the ratio of the areas AB, ACO over BCO over BCO. So we look at this ratio now, ratios of the areas, and we notice that BAO and ABO is simply so BAO and ABO is simply the same triangle. So this area and this area cancel each other. Then CBO and BCO, this is the same triangle, and finally ACO and CAO, this is the same triangle. So they all cancel each other, and we get 1. So this concludes the proof, not of the whole theorem, but of this case, of this particular case. So, but this is kind of the main case. Now, when we have, so this was the case when the lines intersect in a single point and not parallel, and when the points are on the sides and not on the extensions of the sides. So what happens when we have, first when we have the points on the extensions instead of on the sides? Well, so let's say that point, so A, B, C, this is D, this is E, and yeah, let's put it further away. Yeah, it's still well, the CF should be somewhere here, like it would interfere with the previous. Okay, let's draw another picture. So that's the way. So this is C, this is O, this is D, this is E, and this is F. Okay, so they are intersecting at the same point, at the single point, and now if we consider the similar argument with the areas of the triangles, right? So what triangles do we need to consider? So we consider the ratio BD over DC, right? BD over DC. So here this would be equal to the ratio of the, well, first without the vectors BD and DC. This would be equal to the ratio of BOD over the triangle COD. So this remains correct. But then, and for the triangle, the other triangle, like BAD over the area of CAD, this is also correct. But now the step where we subtracted the areas, so the difference between these two areas now is not equal to the area of BAO, because the difference between BAD, so BAD, this triangle, and BOD, and this triangle, and we need to express it somehow with the triangle the area of the triangle BAO. So this would be not the difference but the sum. So the area of B, so the area of the triangle BAO is now equal to the sum of the areas area of BOD plus the area of BAD. And so this is the difference with the previous case. So in the previous case, here we had a minus. Now we have a plus. Now we have a plus here. So that's basically the only difference. But the ratio is again would be equal to the BAO and CAO. Yeah, so basically we can, so the proof is very similar. We just need to be careful about like where we take plus and minus and look at the picture. So the scheme remains, the scheme of the proof remains the same as in the main case, and the details need to be slightly adjusted to remain somewhere plus by minus or minus by plus, but the scheme remains the same. So like I'm not going to reproduce the whole proof, but the idea is the same. So it's so all the other cases are considered similarly. Yeah, so now the case, now we need to consider the case when the three lines are parallel to each other, because in the in the statement we have that it says that intersect at a single point, these lines intersect at a single points, or all three are parallel to each other. And so this is also the case that we need to consider. So if we have so basically let's say that this and this. So this is A, B, C, D, E, F. So the lines, so we have that AD, we assume that AD is parallel to BE and is parallel to CF. And we need to prove that the product of the ratios is again 1, is equal to 1. Well, so here from the parallel lines, so we get, so from this AD is parallel to BE, we get that BD over DC, so this over this is equal to EA over AC. Now to convert it into what we need, yeah, this is true, but we need slightly another quality. So let's write so AE over EC, so this is the ratio that we need, and this is equal to, for the parallel line, so this is equal to GB over BC. This is simply like because of the similar triangles, right? Because the triangle ACD is similar to the triangle ECB. So from the similarity of these triangles, the ratio of sides, we get this. And they're similar because of the because of these parallel lines. So okay, so now we write that BC is equal to BD plus DC. Or maybe we don't even need that. And so now from another parallel line, so from AD is parallel to CF, so let's write this separately. So AD is parallel to CF implies that implies that the ratio that we need AF to FB is equal to DC over BC, right? So basically we expressed both of these ratios, this and this, in terms of the ratio on the side BC. So the product of the three ratios that we need are, so BD over DC multiplied by CE over EA multiplied by AF over FB. So this is equal, so this ratio is equal to, well, it's not equal, it's this ratio, it's the inverse. So BD over DC, we keep it as it is. So now CE to EA, this is the inverse of this, would be BC, replace it with BC over BD, right? So from this equality we replace this ratio, and the third ratio now is what we just calculated. So the third would be DC over BC. Okay, so now we see that BC cancel each other and BD cancel each other, and we get, and DC also, DC and DC cancel each other, and we get just 1. Yeah, so this concludes this case, the proof of this case. So basically we now proved the theorem in one direction. So if the lines are parallel to each other or intersect at a single point, then the product of this ratio is equal to 1. So now the converse statement that suppose that this product is equal to 1. So basically the opposite statement, right? The converse statement. So we assume that. So we assume that BD over DC CE over EA AF over FB is equal to 1, and we need to prove that the lines are either intersecting at a single point or parallel to each other. So what we can do is basically, if two of the lines are intersecting each other, so if neither of the lines are intersecting, then they are parallel and there is nothing to prove, right? So like if all three lines are parallel to each other, then we are done. So if they are not all three parallel, then at least two of them are intersecting somewhere at some point. So let's denote this point O. So this is, let's say this is A, D, B, C, and this is E, and the point F is let's say it's somewhere here. So so then we consider the line passing through O. and we the intersection with the opposite side would be some point f prime. So then we can write the basically the statement for the converse statement that we already proved. So that BD over DC multiplied by CE over EA multiplied by AF prime over F prime B is equal to 1, because for this point F prime, like these three lines, they do intersect at a single point. So from the already proven statement we get this, and now combine it with this, we get basically the first two fractions are exactly the same. So like let's say when we divide one of the equality by the other, so they cancel each other, and basically what we get is that the third ratio must be equal. So AF over FB is equal to AF prime over F prime B. F over F prime B vector. But so from this it obviously follows that F and F prime is the same point, because we can divide the segment AB in a given ratio only like in a unique way. So from this implies that F and F prime is the same point. So let's say like if this ratio, let's say is, well, yeah, like it's clear, like it's a well-known statement that we can divide the segment in a given ratio or in a unique way. So yeah, so this concludes basically the proof. So so F is equal to F prime, and from this it follows that AF, so AD, ADBE and CF intersect at a single point and this point is O, because F prime, like because ADB and CF prime intersect at a single point at C, and if F is the same as F prime, then these three lines are also intersected at the same point. So, and this concludes the proof.